An electric dipole is a type of particle that possesses some interesting properties. If we wanted to build an electric dipole, we would take 2-point charges of equal but opposite charge and place them very close together. Throughout this discussion, we will assume that the distance between the 2-point charges that make up the electric dipole is held fixed. We have already worked with electric dipoles in the first lab in Phi 124L. Another common example of an electric dipole is the water molecule. The water molecule possesses one side that is more positively charged, and the other side of the water molecule is more negatively charged. So even though the water molecule contains 3 atoms in total, to a very good approximation, we could treat the water molecule as an electric dipole. One property of the electric dipole concerns the strength of the electric field created by the dipole. From very far away, the strength of the electric field created by a dipole is approximately zero because overall the electric dipole possesses zero net charge. If you have two charged particles that are very far away from you and very close together, then it is difficult to distinguish individual charges. However, as we move close to the dipole, we would begin to see that indeed those two charges are slightly separated from each other, so we would begin to detect some amount of electric field. Another interesting property of the electric dipole could be illuminated if we consider what would happen to a collection of dipoles that are placed in a background electric field that is constant and uniform. So at this point in the video, imagine you have a collection of some electric dipoles, and then you turn on a background electric field that is constant and uniform. Pause the video and think about how you expect these dipoles to react to you turning on the electric field. When we turn on the electric field, the dipoles themselves will feel zero net force. There will be a force pulling the positive charges in all the dipoles to the right because of F equals QE, but simultaneously there will be a force on all the negative charges in the dipoles pulling them to the left, also because of F equals QE. Because we have two forces that are equal in magnitude but opposite in direction, the net force on all of the dipoles will be zero. Even though the net force on the dipole molecules themselves will be zero, the dipoles are still going to move. Because there is a force pulling the positive charge to the right and the negative charge to the left in the picture as shown, there will be a torque imparted on all the dipoles, and these forces will cause the dipole to rotate so that they align with the background electric field. So how might we use this property of dipoles to our advantage? Let's consider a capacitor, but instead of just having vacuum between the capacitor plates, let's place a substance. We will assume for simplicity that this substance fills the volume between the plates but barely does not touch the plates themselves. This is because we do not want any charges that might be present on the plates of the capacitor to interact with the substance. We will also say that this substance is composed of dipoles that are free to rotate but not free to move around. If we take this capacitor and connect it to a battery, charges will accumulate on the plates of the capacitor. Because there are charges on the plates of the capacitor, that implies there will be an electric field between the capacitor plates. These dipoles now find themselves in the presence of a background electric field and will rotate to align with that background electric field. Because each dipole itself possesses a small electric field pointing away from the positive charge and towards the negative charge of the dipole, there will now be two electric fields between the capacitor plates. One electric field due to all the charges that are on the capacitor plates from the battery, and a second electric field due to all the dipoles being coherently aligned with each other. Because we now have two contributions to the electric field between the plates of the capacitor, the net electric field in between the capacitor plates will be weaker than what it would have been had there just been vacuum between the plates. This implies that we could then place more charge on the plates of the capacitor before the electric field becomes too strong. This material that we placed in between the capacitor plates is known as a dielectric. So how might we quantify what we just have done? Epsilon naught is the permittivity of vacuum. One way you could think about this fundamental constant of nature is this constant determines the strength of an electric field created by 1 unit of charge in vacuum in our universe. you could imagine there is a parallel universe with a different value for epsilon naught, and in that parallel universe, one unit of charge will create an electric field of a different strength in vacuum. In this problem, however, we are not looking at the electric field in vacuum. We are looking at the electric field in a substance. And the way we will handle this is we will multiply epsilon naught by a term k. K is known as the dielectric constant, and K is just going to be a property of the material that you place between the capacitor plates. Usually K will either be given explicitly or will be something that you could look up in a table. As an example, let us consider a parallel plate capacitor with vacuum between the plates. In that case, I would say the capacitance is described by epsilon naught times A over D. If, however, we have a parallel plate capacitor with water between the plates, I would say the capacitance is given by the dielectric constant of water times epsilon naught A over D. Everywhere we see epsilon naught, we replace it with K times epsilon naught. I would then go to a table, look up the dielectric constant of water, and plug it in where appropriate. In the interest of making life confusing, sometimes this term K times epsilon naught is assigned a new constant, epsilon. In that case, I would say that the capacitance of a parallel plate capacitor with water between the plates is given by epsilon of water times A over D. I would then need to go to a table to look up the value of epsilon of water. We said previously that a dielectric material is made of dipoles, but this is not a requirement. It is possible that a background electric field could induce a dipole. Imagine a spherically symmetric atom. You have a positively charged nucleus at the center surrounded by a spherical electron cloud. If we place that atom in a background electric field, the nucleus of the atom, being positively charged, will be pulled in one direction, while the electron cloud, being negatively charged, will be pulled in the opposite direction. I could now say that the average position of positive charge will be offset from the average position of negative charge, and that normally spherically symmetric atom will now behave like a dipole. We have said that there is a maximum electric field that can exist between the plates of a capacitor, and this implies that there is a maximum amount of charge that you can place on the plates of a capacitor. The reason for this is that if the electric field between the plates becomes too strong, then whatever is between the plates, whether it's some type of dielectric material or even vacuum, will become conducting, and then charge will be able to flow from one plate to the other. The value of the maximum electric field that can exist between the plates of a capacitor is known as the dielectric strength. This is what happens during a lightning strike. If there is a large amount of one type of charge in the clouds and a large amount of the opposite type of charge in the ground, there will exist an electric field between the clouds and the ground. Normally air is an insulator, but as more charge accumulates, the strength of this electric field between the clouds and the ground will increase. When the electric field between the clouds and the ground becomes so strong that air changes from an insulator to a conductor, charges will be able to flow between the clouds and the ground. This is what we observe as a lightning strike. The strength of the electric field at which air undergoes this transition from insulator to conductor is the dielectric strength of air. We are considering a parallel plate capacitor that contains a dielectric material between the plates. If this were a parallel plate capacitor with vacuum between the plates, I would be able to write C equals epsilon naught A over D. However, because there is not vacuum between the plates, there is this dielectric material, I need to multiply epsilon naught by K, the dielectric constant. We are given K. That is often going to be the case in problems involving capacitors with a dielectric between their plates. And we are not explicitly given the surface area of the plates, but we are given their length and their width, 3 centimeters and 2 centimeters, and we're told the plates are separated by a distance of 1 millimeter. So I could say the surface area of the capacitor plates is given by 0.03 times 0.02. Remember, we do need to convert all of these distances into meters. So I could say the surface area of the plates is 6 times 10 to the negative 4 meters. And now we are ready to plug numbers in to find the capacitance. I could say C is equal to 3.7 times 8.85 times 10 to the negative 12. times the area, 6 times 10 to the negative 4, over the distance between the plates of 0.001. When I put these numbers into a calculator, I find the capacitance of this capacitor is 2 times 10 to the negative 11 farad. We will now calculate the maximum amount of charge that we can place on the plates of this capacitor. As we discussed previously, there is a maximum amount of charge you could place on the plates of a capacitor because the more charge we place on the capacitor plates, the stronger the electric field will be between the plates, and at some limit, the electric field will become so strong that the material between the plates of the capacitor will break down and become conducting. The way we are going to look at this problem is we will consider a capacitor with some amount of charge plus Q on the top plate and some amount of charge negative Q on the bottom plate. Because the plates of this capacitor are charged, there will be an electric field between the plates and there will be a voltage drop between the plates. These quantities, Q, E, and V, are all related to each other. The connection between the voltage drop between the plates and the amount of charge that accumulates on the plates is given by Q equals CV. The connection between the voltage drop between the plates and the strength of the electric field between the plates is given by V equals E times D. I would like to quickly make 2 comments on this latter equation. First of all, we are allowed to use this equation because we are working with a parallel plate capacitor where the electric field is uniform between the plates. Secondly, I am not including the negative sign because in this example, we really will only care about the strength of the electric field between the plates, and I also did say voltage drop. So looking at these 2 equations, we could say that if we have a capacitor and there is 0 charge on the plates of the capacitor, then I expect there to be 0 voltage drop between those plates. And therefore, if there is 0 voltage drop between the plates, I expect the strength of the electric field between the plates of that capacitor to be 0. If I place some amount of charge on the capacitor plates, there will be some amount of voltage drop between the plates, and therefore there will be an electric field with some strength between the plates. And if I place the maximum amount of charge that can exist between the plates of the capacitor, the drop in voltage between the plates of the capacitor will be at its maximum. If the drop in voltage between the plates of the capacitor is at a maximum, the strength of the electric field between the plates of the capacitor will be at a maximum. The dielectric strength is the maximum electric field that can exist in the material between the plates of the capacitor. We can now begin solving for the maximum charge that can be placed on the plates of this capacitor. We know that the distance between the capacitor plates is 1 millimeter, which was given in the problem. So we could say the maximum voltage drop between the capacitor plates could be written as the dielectric strength times the distance between the plates. Emax is 16 times 10 to the 6, and the distance between the plates is 1 millimeter or 0.001 meter. Therefore, the maximum voltage drop between the plates of this capacitor is 16 times 10 to the 3 volts. Now we will use Q equals CV and the capacitance that we found previously to find the maximum charge that can be placed on the plates of this capacitor. Therefore, I could say the maximum charge that can be placed on the plates of this capacitor is 2 times 10 to the negative 11 times 16 times 10 to the 3, and therefore the maximum charge that can be placed on the plates of this capacitor is 3.2 times 10 to the negative 7 coulombs.